In this short video, we start discussing how you could create your own font, like a font you'd use on a computer, just using parametric curves. And this is going to dive into a bunch of other topics that are above the pay grade of this course, such as vector graphics, things like PDFs, as opposed to bitmaps, which are more like PNG files or JPEGs, as well as what are called Bezier curves that our computer actually uses to write different graphs, or different fonts, excuse me. So these two objects are really what's going to be happening in the background on your computer, but your computer are describing these types of objects using parametric curves. So let's dig into it. So the key things for us to remember that make parametric curves kind of an ideal setting for describing computer fonts is, number one, they are easily scalable. And when I say scalable, I mean we can make them larger or smaller, and they're easy to translate. We can move them around a screen rather easily. We just have to add some desired unit to the X direction as well as Y direction. And what's nice about parametric curves, since each parametric curve depends on a parameter t, we can change the parameter t to make high resolution. So we can do both of these translations and scalability and give out high resolution. So let's just dive into an example. So for those of you who may know, my first name starts with an N, it's Nick. So we're going to try to make the letter N. And we're going to do this using parametric curves. So we're going to consider a XY plane. And we have to try and figure out how we're going to make this letter N using parametric curves. And the main idea that we're going to do is basically break this N into a couple different parts, where each straight line essentially will be associated with its own kind of parametric curve that we're going to piece together through a piecewise function. So for example, if we want to make that left vertical side N, say we start at the point 0, 0, and we go to the point 0, 1. Well, any point along this line segment we could describe in the following manner. So if we call this, say, the first piece, our x of t is identically equal to 0 because our x value does not change on that vertical line. Now our y value is going to change between 0 to 1. So this is where we have something come in. If we're using a parameter t, we could describe any point between 0 and 1 if we let y equal t, but then we have to make sure that our t value is going strictly between 0 and 1. So when t is 0, y is 0. When t is 1, y is 1. When t is 1/2, we're at the point 0, 1/2. Let's try to figure out how we can design a line segment between the next part. And again, we're going to try and make this a piecewise function. All right. So number 2, we're going to have our line go between 0 and 1, say to the next point down here. We could make this N such that this point down here is, I don't know, let's say 1, 0. Let's keep it rather easy. The x value is 1, the y value is 0. So we need to try and figure out every point along this line. So we can do something similar. Well, our x value is going from 0, and it's ending at 1. So we could try to do something like, hey, you know what? let's let x equal t here. And in this case, our y value is going from y equals 1 to y equals 0, since our curve is going that way. Well, if that's the case, we need our y to go from 1 minus t. Now this almost feels right, except our curve is already going between 0 and 1 for t in that first segment. So on this second segment, we need t to go from 1 to some other value. We can say 2. So we need to make sure that our functions, y and our function of x, basically take this into account for those t values. So even though in spirit we're going to be doing much the same thing, in the second part, we need to redefine our t variable to make sure that we're starting and ending at the right place when t is going between 1 and 2 in this second segment. So to do this, we need x to be equal to 0 when t is equal to 1. Well, in that case, we could subtract 1 and see if that works. So if we subtract 1 off of that x value, when t is 1, we're at x equals 0. That checks out. When t is equal to 2, we need x to be equal 1. Well, when t is 2, x is 1. So this seems to work out here. So it looks like maybe if we just subtract 1 off of t, this could work for us. So in this second segment, if we're subtracting just 1 off of t, we need to make sure that we have parentheses around that t variable, since we're essentially going from t to t minus 1. So let's check this. When y is equal, or when t is equal to 1, our y value now is equal to 1 minus 1, or minus 0. So that checks out. When t is equal to 2, in the second part, well, we get 1 minus a 2 minus 1, or 0. So that checks out as well. So let's just summarize what we've found so far. And I'm going to erase some of this top stuff. So far what we've found is that our x equation can be written as a piecewise function where x is identically equal to 0 for t values between 0 and 1. Then we found x is equal to t minus 1 for t values between 1 and 2. We found something similar for y. Y is equal to the piecewise function of t when t is between 0 and 1. And it's equal to 1 minus t minus 1. In other words, it's equal to 2 minus t. When t is between 1 and 2. So now we just have this third section to go. And in this third segment, well, we just need n to go between, say, this point on the x-axis and this point up here, which we could make is equal to 1, 1. Again, we're defining our own font. So we need this curved trajectory to go from the point 1, 0 to the point 1, 1. So let's try to figure out what that function needs to be. So in this third segment, our x value is going from, well, it is going from 1 and staying equal to 1. So it looks like no matter what t value changes between those 2 points, our x value is always equal to 1. What's happening to y here? Well, it looks like y is going between 0 and 1. So if we were to define t again between 0 and 1, this would be fine. But since t has already gone between 0 and 1 and then 1 to 2, we need t to go between here from 2 to maybe some other number, which we could just make equal to 3. So if t is going between 2 and 3 here, we could subtract 2 off so that when t is equal to 2, our y is 0. Then when t is equal to 3, our y is equal to 1. So we can define our x value to be equal to just 1 whenever t is between 2 and 3. And then similarly, our y value will be t minus 2 when t values are between 2 and 3. So these two functions, our x of t equation and our y of t equation, those parametric curves give us this letter n. So if we're working on a computer and using a font, we basically just made up a font for the letter n. If we wanted to be real fancy, we could of course add some extra flares onto this function. Say something like, I don't know, maybe the n on the side has a little flare like this, and at the beginning has another flare, so our n kind of does something that looks a little fancier. We could start defining fonts if we wanted this way. We're using straight lines here, but there's no reason we couldn't start adding curves between points. Maybe we could make a font that does something a little bit groovy for our letter n. But the big idea is we can define between points any parametric curve we want, and we can piece them together using a piecewise function to give us a specific font or a specific parametric curve for that particular letter. And we could do this for every letter of the alphabet and then just define our own computer font in this manner.